Okay, let's look at one solution for problem number 5 on the take-home quiz for building a binary multiplier. So the idea for this problem is that I'm multiplying two binary numbers. So say, for example, 7 times 6. And binary multiplication works just the same way as I do decimal multiplication. I'm going to look at each digit from the multiplier and multiply that digit times the first number, or we also call this the multiplicand. And then I add in a 0, look at the next digit, multiply it towards the multiplicand, and so forth and continue on. In the case of binary, it's the same thing, except now I just have zeros and ones. So 0 times 1, 1, 1, I get 0, 0, 0. Put in a 0 in that first position. Now I have 1 in the second bit position, so I have 1, 1, 1. Then I have 2 zeros, and then the most significant bit's a 1, so again I have 1, 1, 1. And then I'll add up all these partial results to get 1, 0, 1, 0, 1, 0. Okay, so this is with n equal to 3. If in general I have two n-bit numbers that I'm multiplying together, then I'm going to need at least 2 to the n bits for my resulting product. Okay, so to build a sequential circuit that does this multiplication, I'm definitely going to need an adder, and I can use a register for storing the multiplicand, the multiplier, and also my intermediate sums or the product. So one idea here would be to just repeatedly add the multiplicand to this partial product, and then I'm just going to keep shifting the partial product so that the addition of that multiplicand is always occurring in the same place. So I could build this circuit, given I know my product's going to have 2 to the n bits. My multiplicand and multiplier are only n bits, but my adder and my product or my partial product register holding the intermediate results would both have to be 2 to the n. But that's a lot of hardware, and I'm going to go ahead and implement this with a little optimization. So for example, with my register A and Q, I'm going to initialize the partial product to just 0, and my Q register will initially hold the multiplier. Now I'm going to look at the least significant bit of Q, the multiplier, to tell me if I need to add the multiplicand or the value in register B to my partial product. So in this case it's a 0. I don't. And so what I'm going to do now is shift A and Q to the right 1-bit position. And in this case I'll shift in a 0 into the most significant bit. Okay, now the least significant bit of the Q register, which is the next bit of my multiplier, is a 1. So I'm going to add 1 to the A register, which in this case now, these 4 bits are holding my partial product. So I'm going to get 1, 1, 1 with no carry. I'll go ahead and write the carry over here. Now I'm going to go ahead and shift again to the right, this time putting the carry into the most significant bit. So now I have 0, 1, 1, 1, 0, 1. And now I'll do the same thing again, and I'll check the least significant bit of Q, which is now holding that last bit on the multiplier, and it's a 1 again, so I'm going to add 1, 1, 1, the multiplicand, again to the register A. This time getting the following, 1, 0, 1, 0. And so now I'm going to shift one more time to the right. And so now I've done this 3 times, the number of bits in my multiplier, checking the least significant bit, seeing if it's a 1 or a 0, adding the multiplicand, and then shifting, and I see I get the result is the same what I got above. Okay, so my hardware for this, I'm going to have the 3 registers, B holding the multiplicand, Q initially holding the multiplier, but at the end of my sequential circuit execution, it's going to hold the least significant bits of my product, and register A holding the most significant bits at the end of the product. So my adder is an n-bit adder, but this register A, in addition to being a normal register with a parallel load, is also going to be a shift register. And the same thing for register Q, it's also a shift, specifically a shift right. And then I also have to take into account the carry, which gets shifted in the most significant bit. Okay, so the last thing I'm going to need for this circuit, though, is a finite state machine or a control unit that's going to actually decide when these registers are loading and shifting and so forth. So the control unit will output 4 control signals, controlling when the registers load, shift, or clear their values. And the control unit's going to take as inputs the least significant bit of the Q register, as well as a signal telling us when we've done the number of steps. So I'm also going to include a counter, and I'll have a simple combinational block to tell me when I've hit 0 on that counter. And we'll call this signal Z that goes in the control unit and tells us when we've reached 0 on our counter. I can also include an external signal for starting the whole thing, and call this the go signal, or G, and the counter will obviously be initialized when we're starting over with the value of n-1. Okay, so given this hardware and the layout, let's look at how we could actually control this and build the finite state machine to control this. So I'm going to have an initial state or an idle state where I haven't started yet, and I'm going to stay here as long as the go signal hasn't been inserted yet. But as soon as the go signal is inserted, I'm going to start the process of multiplication. And when I do that, before I get into the next state, I also want to initialize all my registers. So for example, C will get the value of 0, A will be initialized to 0, and my counter P will be initialized to the value of n-1. Okay, so in the first multiply state, what I'm going to check is the least significant bit Q0. And if Q0 is 0, then I'm not going to add the multiplicand value to register A, and instead I'm going to go ahead and just go on to the next state, where I do the shift. But if that least significant bit is a 1, then what I really want to do is add A and B and put the result in A, and also save the carry out into that flip-flop C. Okay, so now in the second multiply state, mul1, I'm going to look at that Z signal to see if my counter has reached 0 yet. If it hasn't, then I'm going to just do the same thing all over again. But if it has reached 0, then I finish my multiplication and I'm going to go back to the idle state. In either case, in this mul1 state, this is also where we're going to do our shifting. So if we treat the carry, flip-flop, the registers A and Q as just a single register, what we're really doing is shifting all those bits to the right one position. We're also decrementing the counter and resetting the carry flip-flop to 0. Okay, so now for the control unit, which is actually going to output the control signals, which will control what happens with all of our registers, let's go ahead and write down what the design for that would look like. So for my register A, if I look at the micro operations that I'm doing for it, I'm clearing it, I'm loading the value with the result of the add, and I also am shifting it. For register C, I'm either clearing it or loading it with the value which is from the carry out of the adder. For register Q, the only thing that it's doing actually is shifting right. Well, in addition to loading the initial value of the multiplier at the very beginning, which also happens for register A. For register P, the counter, I'm either initializing it with n-1 or just letting it count down. So the control signals that I'll need are going to have to be initialize, which is shared for these registers. I'm going to have a load control signal, and then I'm also going to need a shift control signal. Well, I'm going to go ahead and call this shift decrement because I'm also going to decrement the counter whenever I shift. And actually I'll include, for the clear of the C flip-flop, I'm going to give this its own control signal because this is only occurring in one place in my state diagram when I'm in state mul1. Okay, so now I have these control signals. I can write Boolean expressions for the control signals. So the initialized control signal is a 1 when I'm in the idle state and the go signal is 1. The load signal is 1 when I'm in the multiply 0 state and the least significant bit of the multiplier, which is in Q0, is a 1. That's the only time when I'm going to do the loading or the addition. The shift always happens in the mul1 state, as well as the decrement. So that's an easy expression. And then the clear of that C flip-flop, which holds the carry, happens when I first initialize. So it has also when I'm in idle and the go signal is 1, or it will also be set whenever I go into state mul1. Okay, so now we can go ahead and implement this control unit or finite state machine, and I'm going to implement it with a sequence register and a decoder, which is basically what we've done before. where we're going to write out the next state table, come up with the Boolean expressions, but I'm also going to use a decoder before I generate the final control signals, in this case, these 4 control signals. So I have 3 states in my diagram. I'm going to need at least 2 flip-flops. I have 2 inputs, G and Z, and I'll go ahead and use D flip-flops for my design. And I'll assign the states where 0, 0 is the idle state, 0, 1 is mul 0, and 1, 0 will be the second multiply state, mul 1. Okay, so when I'm in the idle state, I'm going to stay in that idle state if G is 0. Doesn't matter what the Z value is. But if G is 1, again, doesn't matter what Z is, then I'm going to go on to mul 1. Sorry, mul 0. So 0, 1. When I'm in mul 0, I always unconditionally go on to the next state, which is mul 1. And G and Z don't matter. And when I'm in the mul 1 state, it depends on Z. So if Z is 0, then I go back to mul 0, 0, 1. And if it's a 1, then I go back to the idle state, 0, 0. So I can write expressions now for D1, which is just 1 when M0 is 1. And D0 is a 1 when I'm in the idle state, or M1 and M0 are both 0. And G is 1, or when I'm in the mul 1 state and Z is 0. So the circuit would look like this.